we said that in order to find out the different isotopes of an element and their percentage abundances, we use an instrument which is called the mass spectrometer. Okay, Matthew?
Yep.
Okay, now what is this mass spectrometer? How do we use it? In order to find out the number of isotopes and the different abundances of any element, we start to introduce our element from here. We put our element here from this opening, and then our element is going to be subjected to a heater, where this heater will make our sample in the vapor state. It will change our sample from the liquid state to the vapor state. So we are going to heat our sample, we introduce it from here, and then we are going to heat it electrically so that it transfers from the solid or the liquid state to the vapor state here. Okay, now this is our sample. If we see that this is our sample, which is now in the vapor state or in the gas state, now we are going to subject it to a highly energetic beam of electrons. Highly energetic beam of electrons. This is the beam of electrons that we are going to subject our sample with. Now we introduce our sample from here, we heat it electrically until it turns into a gas, and then we subject it to a highly energetic beam of electrons. Now, what happens to our sample when it is subjected to this beam of electrons? Whenever something, yes?
It becomes an ion.
It becomes?
Ion.
Yes.
Like an ion.
You mean it is going to be ionized, isn't it?
Yeah.
Yes, excellent. It's going to eject an electron, and itself is going to form a positive ion. So now we have our gas element. We are now introducing an element. We will find that our gas element will be ionized into a positive ion because an electron will be ejected as the gas sample is subjected to a beam of electrons. Whenever something is subjected to be collided with an energetic beam of electrons, an electron is emitted and the sample itself will be ionized to a positive ion. Okay, now here, this is our sample that is positively charged. It contains a positive ion here. It's present here. Now, then it's introduced to an electric field. It is introduced to an electric field. What is the electric field? It means that we are going to introduce two plates in front of our sample, positive ion, where one of them is negatively charged and the other is positively charged. So what is going to happen is that our positive ions here are going to be attracted strongly to the negative plate of the electric field. And as it is attracted strongly to this plate, it's going to pass through a hole here inside this plate. It's attracted strongly, and so it will pass through this plate where it is introduced to another plate which is positively charged. So repulsion will take place between the positive ions that are here now and the positive plate, and so they can move inside the mass spectrometer. So the use of the electric field accelerates the ions. Of course, you are not, yes, excuse me?
How does the positive plate accelerate?
It is accelerated as it is first attracted to the negative plate and then repelled by the positive plate. So this makes acceleration to the ions, because at the beginning it was attracted strongly to the negative plate. When it passes through this hole, as it is attracted, then the positive hole repels it, because we know that different ions attract and similar ions repel. Different charges attract and similar charges repel. So it's accelerated to move through the mass spectrometer due to the presence of this electric field, where the negative plate will attract the positive ions that are formed from our element, and then the positive plate would repel it, and so the positive ions are found here in this medium, okay, at this place. Understand, Matthew?
Yes.
Okay, now there's another part in the mass spectrometer, which is the magnet, which supplies a magnetic field. It supplies a magnetic field. Okay, what does the magnetic field do?
It creates a pulse.
Yes, it creates a pulse and it's going to deflect the positive ions. The magnetic field deflects the positive ions formed. It's going to deflect it depending on two factors. Depending on two factors. What are these factors? The first factor is the mass of the ion, and the second factor is its charge. Okay, so the magnetic field is going to deflect the positive ions formed depending on two factors, the mass of the ions and the charge. Now we said that we are introducing here an element. And as we said from a moment, that element consists of different isotopes, isn't it?
Yes.
Then each isotope has a different mass. Because, for example, when we say that we have different isotopes, neon, for example, 20, neon 20, for example, neon 21 and neon 22, for example, we have 3 isotopes of neon. Each one of them now is in the form of a positive ion. These 3 isotopes are going to be present here. All the different isotopes are going to be present here to be introduced to the magnetic field. Now, these 3 isotopes are found here together, but when they are subjected to the magnetic field of the magnet, each ion of these is going to be deflected by a different degree depending on its mass. Okay, so the magnetic field will separate the different ions, will separate them from each other. The neon 20 will separate from the neon 21 from the neon 22. If, for example, in this example, we have 5 isotopes, then they are going to be separated into 5 different lines, depending on the magnetic field that they are subjected on. They are dependent, their separation depends on the difference in mass of each ion from the other. So, of course, we have neon 20 has a less mass than neon 21 has a less mass than 22. So what do you think? Which one of them is going to be deflected the most?
Oh, 20.
Yes, excellent. So the lower the mass, the lower the mass, the greater the deflection. The lower the mass, the greater the deflection. Okay? Now, for the charge, now we stated that this charge, when we subjected our element in the gas state to the beams of electrons, then an electron is ejected and it forms a positive 1 charge. The charge, we are always going to say that the charge is nearly always plus 1. But sometimes when the element is subjected to the beam of electrons, 2 electrons are emitted and we get a plus 2 charge. Instead of a plus 1, we get a plus 2 charge. Okay, so in this case, if our charge or the charge of one of the components or one of the isotopes is plus 2, then what happens? It will be deflected more by the magnetic field. So the more the charge, the greater is the deflection. Okay, Marcus, Okay, Matthew?
Yeah, but I have one question.
Yes,
Why do you need to subject the sample to a highly energetic beam of electrons? Because it doesn't seem like it has any use.
it doesn't seem it has any.
It is not very useful because
You mean that we don't need to subject it to beams of electrons?
yeah, because uh, for isotopes of the same element, they all gain the same charge, so it's not like giving it a charge will affect it.
Yes, but we said that sometimes they form a different charge when they are subjected to the magnetic field. When they are subjected to electrons, sometimes it produces a different charge, and charges allow them to go through the mass spectrometer itself. I want them to go here. I want to accelerate them. I want them to move inside the magnetic field, to go through the magnetic field. So this acceleration will not take place except if we encourage them to go inside. So how do we encourage them? We encourage them by forming positive ions and then subject them to an electric field in order to accelerate their movement. Okay, I want them to be accelerated inside here. What will make them be accelerated inside the mass spectrometer is that they are forming a positive charge. And on the other hand, as we said, that we want to separate the isotopes not only depending on their mass, but also depending on their charge. Some of the elements would form a +1 charge and others would form +2 charge. That's because on using the mass spectrometer, we don't only determine the isotopes of different elements, but at the end of our course, we will find that we can use the mass spectrometer in order to find out the different fragments inside a molecule, an organic molecule. And this organic molecule, when it forms ions, these ions could be in the form of +1 or +2 charge. So we have to use we have to subject them to the beam of electrons to form these positive ions, either +1 or +2, in order to accelerate them inside the mass spectrometer, to let them move inside the mass spectrometer, urge them to move inside the mass spectrometer, and then their separation also depends on their different charges that are formed.
But even if they don't have a different charge, they still get separated. So
yes, they are going to be separated by mass only, by depending on the property of their mass only. But sometimes we need more separation. We need more separation because the mass will separate them, yes, but also the charge would separate them more. It could separate them depending on what is the charge that they can form. They can form +1 or +2 charge. So depending on the charge also, we can make more separation.
okay, yeah.
Okay, so we have to depend on these two factors. In your course, yes, in this course, yes, we say that most of the ions formed will be in the +1 charge. But in organic molecules, they can form either the +1 or the +2 charge, and in that case, they can be separated more and more. We can get more separations. In organic molecules, we don't have simple mass spectrogram as in case of elements. In case of elements, we get only a few lines, which we call peaks, as we are going to see now. But in an organic molecule, we will get many lines, we get many peaks, and we have to determine every peak, what does it correspond to. So we should make more and more separation for more and more fragments. Okay?
Okay.
That's why we should depend on mass and charge as well. So in this course, in the AS course, we are going always to say that the charge is equal to +1, except if he tells us that it is +2. Because sometimes in some problems, he will say that our charge here is +2. So we have to deal with this. But if he doesn't say that we have a +2 charge, then we are going only to say that the charge always is equal to +1. And this means that we depend on the mass only. Okay, Matthew? Okay, now here, as we said, if we have different isotopes that are going to pass through the magnetic field, then they are separated, they are going to be separated depending on their mass and depending on their charge. The lower the mass, of course, is going to be deflected more than higher mass or greater mass. And the more the charge, also it's going to be deflected more than the lower charge. This means that the +2 charge is going to be deflected more than the +1 charge. And then it reaches what we call, thank you, and then it reaches what we call a detector. The detector is moving from one peak to another, from one line to another, from one deflected positive ion to an ion in order to detect it. And then the detected species using a computer, they are going to be amplified, and then we get what we call a chart recorder. Okay, in the chart recorder, I'm going to rub this first. In the chart recorder, we get a spectrogram. We call this a spectrum. We call it a spectrum, mass spectrum. We get a drawing or a graph that is drawn between these, the relative abundance or the percentage abundance against the mass over charge ratio. So here, the mass spectrum, we call this a mass spectrum that we get in our computer. We get a recording chart drawing the mass over charge against the percentage abundance or sometimes the relative abundance. So since we said that most of the charge that we are going to deal with in the AS course, most of the charge is a +1 charge. And this means that mass over 1 means that we have only mass. So any peak, we call these peaks, any peak that we obtain here is the mass of one of the isotopes. And it is drawn against the percentage abundance or the relative abundance. So this is the mass spectrum of neon. For example, we find that we have 3 peaks, we have 3 different peaks, even if this peak is so small, but we count it. And this means that when we have 3 peaks, this means that we have 3 different isotopes. We have 3 peaks, we have 3 different isotopes, okay? And these are the percentages abundance of each. Now the isotopes of neon, as you see here from this spectrum, are neon 20. We get, of course, the 20 from here. We have neon 21, and we have neon 22. And we will find that the percentage abundance of neon 20 is 90.9, that of neon 21 is 0.3%, and that of neon 22 is 8.8%. Okay. Now we got our mass spectrum from which we can deduce the 3 isotopes of neon, and from which we can calculate the relative atomic mass of neon, which is equal to, as we said before, 20 times its percentage, which is 90.9, plus 21 times 0.3, plus 22 times 8.8 divided by 100. Okay, so from which we can calculate the relative atomic mass of neon. And of course, we should find it very near to 20 because it is the maximum percentage. So we will find, if we look at any periodic table, we will find that it's the relative atomic mass of neon. I'm going to look here. It's 20. It's written, it's 20 because Of course, it's not going to be 20 exactly, but we will find that it is very near to the 20 because most of the percentages of isotopes of neon is found as neon 20. Okay.
Okay.
Now, yes,
For the electrons,
yes,
suppose neon 20 only has a +1, neon 21 has +1, but then neon 22 has +2.
yes.
Wouldn't that make the relative atomic mass like wrong? Because you can't say that the mass of neon 22 is 11 because that's 22 divided by 2.
Yes, yes, of course. If you find that it's if you find that there is a big difference, you are entering an element, and if you find that you have a mass, as you said, if one of them has a +2 charge, this means that the mass here will be equal to 10, for example, isn't it?
Yeah.
So you will find that there is a great difference between these values and these values, and this means that this ion is present in the form of +2. Why? Because this is an element. An element means that all the atoms are of the same type. All the elements are of the same kind. Okay? And usually the +1 charge is not drawn with the +2 charge. You will find that if they are present, you will find that we have a very much lower amount of mass here because it is a mass over 2, from which you can deduce that this is a +2 charge. Then you have to multiply it by 2 to find out the correct mass. Okay? Because it's an element. All of it is formed from, it doesn't contain impurities. It's an element. You always make your mass spectrum with pure elements. And so you are not going to get different masses except when you have different charts on them. And the second thing is that you are subjecting all of your elements to the same amount of energetic electrons. So they will always produce the same charge because when you bombard or when you collide your element with the beam of electrons, usually an electron is emitted. But if they were very highly energetic, then it can produce the +2 charge.
Okay, but if all of them have a +2 charge,
Yes.
that would mean their relative atomic mass is twice the
Yes.
actual one.
Yes, exactly.
So would you have to divide it by 2 again if it's +2?
Now, if he says that the charge is +2, if he tells us that the charge is +2, then any number here, 20, means it is the mass over 2.
Yeah.
And this means that the mass is equal to 40, not 20.
Yeah. So you always have to times it by 2 if the charge is +2.
Yes. If the charge is +2, this is the charge. And this is the mass. So if he says that the charge was +2, then you have to divide by 2 to get your mass.
Okay, but in this chart, it doesn't say whether it's +1 or +2.
No, so, because yes, if he doesn't say, then we always assume that it is +1 charge.
Oh, okay.
Except if he says it's +2, then we have to divide by 2. But if he doesn't say, then we assume that it is +1, because in most cases it should be +1. In most cases.
Oh, okay. Yeah, I understand that.
Okay. Now, if we look to another mass spectrum, that of zirconium, for example, zirconium, we will find how many peaks for zirconium?
5.
Yes, we have 5, and this means that we have 5 different isotopes for zirconium: zirconium 90, zirconium 91, zirconium 92, zirconium 94, and zirconium 96. and from the relative percentage abundance, we can calculate also the relative atomic mass of zirconium, as we did for the others, as we did here for example, neon or any other element. Okay.
Yeah. Okay.
Now, here, up till now, we have seen the mass spectrum of monoatomic elements. As you know, that elements are divided into monoatomic and diatomic. And of course, we have phosphorus and sulfur, they are different. But most of the, all of the metals and the inert gases, they are formed from only monoatomic elements, only one atom. And so in this case, the peaks that we obtain are the number of isotopes, and from which we calculate the relative atomic mass of whether neon, zirconium, or whatever, any metal or any inert gas. But sometimes our elements are diatomic. They are diatomic like chlorine.
Yeah.
The mass spectrum of chlorine element. Okay. Now, chlorine is a molecule. It's not a simple atom. It consists of two atoms of chlorine. And we said at the beginning that we have two isotopes for chlorine atoms. We have chlorine 1735 and we have chlorine 1737. And these two are present in the 75% percentage abundance and 25% percentage abundance, or we can say that they are present in the ratio 3:1. Okay, now for chlorine molecule to be formed, it can either be formed from two similar chlorine 35 isotopes, and this would produce chlorine molecule, which is 70. Okay, yes. Chlorine molecule can be formed from two similar chlorine 35, or it can be formed from one atom, chlorine 35, one isotope, and the other is the chlorine 37. So we get chlorine 72. Or it can be formed from both chlorine atoms, could be from the isotope chlorine 37, and in that case, we get chlorine 74. Okay?
Yes.
So what will be our spectrum? Now, this is a molecule. Chlorine here is a molecule.
Yes.
And whenever we have a molecule subjected to the beams of electrons, always we get our mass spectrum when we draw the mass over charge against the percentage abundance against the mass over charge. We always get at the end what we call the molecular ion peak. We get something called the molecular ion peak, which determines our molecular mass. We get this, we call it the molecular ion peak. From the molecular ion peak, we usually get our molecular mass of the molecule.
Okay.
Okay. Now, here in case of chlorine, we know that it is an element. We know it is not an organic compound because the organic compound will differ from the elements. So since we are introducing inside our mass spectrum, spectrometer, we are introducing an element, which is chlorine element, we are going to find that we get three peaks, one of them at 70, the second one is at 72, and the third one is at 74. We get three peaks, one at 70, one at 72, and the other at 74. And these are in the ratio 9:6:1. We are going to see what's 9:6:1. Okay. Now, the second step is that when we were subjecting our chlorine element to the beams of electrons, we said that either an electron is ejected and chlorine forms the Cl2 positive, Or else, since this is a molecule, then it's going to be broken into its atoms, which are the chlorine atoms. We call this fragmentation. It's going to be broken into its two atoms, two isotopes, which are the chlorine 35 positive and the chlorine 37 positive. The chlorine molecule is going to be broken by the beam of electrons, and or we can say that it is fragmented or broken into its simpler formula, which are the atoms, simpler form. Okay. Now we said that chlorine 35 is present in the ratio 3:1 for the chlorine 37. So we get two other peaks, one of them at 35 and the other at 37. Of course, this graph is not drawn. We make like this to show that this is not, they are not continuous. These numbers are not continuous. So we get here a peak at 35 and another peak at 37 in the ratio 3:1. Okay. Now we know that the ratio between 35 to 37, chlorine 35 to chlorine 37, is in the ratio 3:1. Okay. So this is the ratio. That's why we got here these two peaks in the ratio 3:1. But now for these chlorine molecules that formed, where we got our molecular ion peaks, it means the molecular mass of the element, we got three peaks in the ratio 9:6:1. Why do we get this ratio?
When you do 35 and 37, because there's two of them, you square the numbers, so the ratio is 9:1.
If you, would you, excuse me, would you repeat?
For chlorine 35 to chlorine 37, the ratio is 3:1.
Yes.
And since there's two of them together, because it's diatomic,
yes,
you square the number.
Yes.
So it's 9:1.
Okay. 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 What you're saying is correct. Yes, but we have to do some calculations, because usually they say, how do we obtain this? They want us to make some calculations. Okay. So we say that when we have chlorine 35 to chlorine 37 in the ratio 3:1, then the total probability will be 4, isn't it? And this means that chlorine 35 is formed with the probability 3/4. And chlorine 37 is formed with the probability 1/4. Okay, so if we talk about the first probability, we said that the first chlorine is 35, and this means that its probability is 3/4. And the second chlorine is also 35, then the probability of its formation is also 3:4. And so we get the total probability of the formation of chlorine 70 is 9:16. Okay, now for the second probability here, either the first atom or the first isotope is 35, so its probability is 3:4. And the second chlorine is isotope 37, then it's 1/4. Or else the opposite takes place, that the first one is 37 and the second is 35. And so their sum will be 6/16. Now, for the third probability, both atoms or both isotopes are 37, and this means 1/4 times 1/4, and we get 1/16. So the ratio between chlorine 70 to chlorine 72 to chlorine 74 is in the ratio 9:6:1, because all of them divided by 16, then it's going to be 9:6:1. This is the ratio that we get. Okay, Matthew? Is that what you were saying?
Yeah.
Okay. But we have to show it, because they always say, show your working. So you have to do it in this way. Now, the second element that we should know is that of bromine. The mass spectrum of bromine. And of course, bromine, we will do exactly what we did in case of chlorine, but the only difference is that bromine has two isotopes, bromine 79 and bromine 81.
Yep.
And these two isotopes are present in 50% each, around 50%. It means that they are present in the ratio 1:1. Okay, so also we are going to do the same. We are going to say that either both bromines are formed from the isotope 79, and in that case we get the bromine molecule, which is 158, no, 158, or else one of the bromine isotopes is 79 while the other is 81, and in that case we get the bromine, which is 160. Or the third is that both of the bromine atoms are of the isotope 81 to form the bromine molecule 162. Okay?
Yep.
And then, as we said, that the bromine molecule is going to be broken into two bromine atoms. One of them is the isotope 79 and the other is the isotope 80. All of these, of course, are positive ions because in the mass spectrometer, we get always positive ions, as we said before. So here in this spectrum, in this mass spectrum of bromine molecules, we get the mass over charge, and here we get the percentage abundance. And we will find that we have 3 bromine molecules. We get 3 peaks.
1 to 2 to 1.
Yes. One at one at what?
1 to 2 to 1.
One at 158, isn't it?
Yeah.
The other at 160, and the third at 162. Yes, exactly. So we have 3 peaks, one of them at 158, which is the molecular mass. We call them molecular ion peaks. They give us the molecular mass of the element. So we get one peak at 158 corresponding to the bromine molecule of 158. We get the second one at 160, and the third at 162. And here the ratio is 1. Yes, 1 to 2 to 1, as you said. The ratio is 1 to 2 to 1. And then we get 2 other peaks, one of them at 79, okay, and the other at 80 also. No, this is 81, not 80. The other one at 81, but in the ratio of 1 to 1. So we get 2 peaks at 79 and 81. They are in the ratio 1 to 1 because both isotopes are present in the same percentage in nature. Their abundance is 1 to 1. So also here, to do this calculation, then we will say that the sum of these two ratios, 1 to 1, then their sum is 2. And this means that the probability of the formation of each one of them is 1/2, or half. So if both bromine atoms were of the isotope 79, then the probability of their formation is half times half, and this makes 1/4.
Yeah.
For the second probability, we have the first one also half times the second, which is half, or else we say that the first one was 81 and the second was the bromine 79. So it's also half times half. So we get 2/4. And the third probability that both are 81 is half times half. We get it 1/4, isn't it? So
Yeah.
this means that the ratio is 1 to 2 to 1. This is our ratio that we got here, 1 to 2 to 1. And here only, since both of them are in the same ratio, then we get 1 to 1 ratio. So this is the mass spectrum of the element bromine. Okay. Now for an organic molecule, we said that we are going to take this at the end of our course, but we should have only a small opinion or a small information of what happens is that in organic molecules, the mass spectrum is that, as we said here, that when we draw the mass over charge against the percentage abundance, we get the last peak here. In the last peak here, it shouldn't be always high. It could be very small. It could be very short. We get what we call the molecular ion peak, which shows us the molecular mass of the compound. So our molecule is subjected to the beams of electrons, and at the first step, we get our molecule positively charged, and this gives us its molecular mass. But then this molecule, upon more subjection to more electrons, is going to be fragmented. It's going to be fragmented, or fragmentation will take place for this organic molecule, and we get two simpler molecules. One of them is positively charged and the other is a free radical. We call it a free radical. Now the one with the positive charge is going to have a peak here in our spectrum. We are going to have a peak here. Or else we say that the fragmentation will take place if this is A and this is B. It could be A that has the positive charge and B will have the free radical. And so we get also a peak for A. So upon fragmentation, we get a lot of peaks depending on the type of fragmentation that takes place. But the last peak is always the molecular ion peak. And also we have the tallest peak. If we have the tallest peak, we call it the base peak. We call this the base peak. The base peak is the peak that has the highest percentage. And the molecular ion peak is the molecular mass of the compound. Okay, and of course, as I told you, organic molecules are going to be dealt with at the end of the course. Okay, Matthew, do you have any question?
No.
Okay.
Wait, actually, if molecular ion peak.
Can you raise your voice a little bit, Matthew?
Actually, it's fine. It doesn't matter.
No, please ask what you want to ask.
No, I think I know the answer. Fine.
Okay, because I don't know why I can't hear you clearly. Your voice is clear, yes, but it's too low. So.
Oh, yeah, it's fine. Sorry.
Okay, yeah, thank you.
I'll speak louder.
Yes, okay. So that's all what we have taken about the mass spectrometry of simple molecules or simple elements, from which we can calculate the relative atomic mass or the relative molecular mass of compounds. And as I told you here, can you see the screen?
Yes.
Okay, as I told you here, in case of an organic molecule, we will get, this is the mass spectrum of the organic molecule. It contains a lot of peaks, but we usually choose which peaks that we are going to deal with. We don't always define every peak in the mass spectrum. No, we can't do that. We take only certain peaks and try to find out what are these fragmentations. As you see here, this is the last line. This is the molecular ion peak that is denoted by M. It means that this is the molecular mass of the compound. And we have other peaks. Sometimes we have peaks only smaller by 1. And this means that only a hydrogen atom gets out. Okay, we don't deal with every peak in the mass spectrum. We take only certain peaks to determine the structure of our organic compound.
Okay, so how do you determine the structure now?
How can we?
How do you determine the structure with all of this data?
Yes, in organic compound, whenever you prepare an organic compound, this is a new organic compound, you want to determine its structure. Of course, you make different studies, you make different tools, not only mass spectrum. You get what we call its infrared spectrum, its UV spectrum, its mass spectrum, whatever. We have a lot of course, we make elemental analyses, and from all these, we gather our information to determine the structure of our molecule. So from mass spectrum, we see, for example, because this is not here, you want to get more answers, but this is at the end of your course. For example, if you have a molecule like this, for example, if I have a molecule like this means that if I have propane and then I put it in the mass spectrometer, then at the beginning, I'm going to get the molecular mass of the compound as a whole. So this is 3 carbons makes 36, and we get it, yes. So it's 44. So at 44, you are going to get the molecular ion peak. Then what happens is that this molecule is going to be broken.
Okay.
So either you get, when it is broken, either you get a CH3 positive, and the rest of the molecule is in the form of a free radical, we call it a free radical, or else it can be broken into CH3 free radical and you get CH3, CH2 positive ion. So this positive ion will give you a peak at 15. You see, here is a peak at 15. It's very small, but it's present. Okay. Of course, this is not propane. This is not propane, but I'm just telling you how the spectrum will appear. And then the molecular mass, okay, would you excuse me for 1 minute, Matthew?
Okay.
1 minute on.
Okay.
Okay, Matthew, sorry.
Okay, it's fine.
Okay, so the second peak will appear at 29, which is the molecular mass of CH3, CH2 is 29. So we will find that we have a peak at 29, for example, here, and so on. You do the fragmentation from every point and see every point would lead to what?
Okay.
You make fragmentation to your molecule. For example, if you have like this, CH3, CH2, C double bond O, CH3, then you make the fragmentation here and you have either this as positive or this as positive, and then you make another fragmentation here and see this is altogether is a positive. You calculate its molecular mass. So you see every peak from here, what does it correspond to the fragmentation in your molecule?
Oh, okay. Do these fragmentations happen in the same ratio?
No, they don't happen in the same ratio, no.
Oh, okay.
Sometimes,
yeah, okay.
Sometimes you do not get a certain fragmentation. Sometimes you do not get it at all. And sometimes you get it. Okay, and as I told you here, this is called the base peak.
Yeah.
This is called the base peak. It means it's the highest peak in the spectrum. And of course, this highest peak corresponds to the most stable positive ions that can be formed.
Oh.
Okay.
Oh, yeah. Okay.
Okay, sometimes you get here, beside the molecular ion peak, you get a very, very, very small peak at m+1. It means after the molecular mass by 1. What is this?
Yeah.
We call it the m+1 peak. It's because in organic molecules only, they are formed from carbon atoms. And carbon atoms, we said that we have two isotopes, carbon 12 and carbon 13. The difference between them is 1, isn't it? We have carbon 12 and we have carbon 13. And the ratio between them is 99% to 1%. So the difference is only 1, and the percentage of carbon 13 is very, very, very small. That's why you get a very small peak here, which is the m+1 peak. It means that maybe one of all these carbon atoms that were included in your organic compound was of the carbon 13. Okay?
Okay.
Of course,
So,
this is, yes.
So would the m+1 peak be your molecular ion peak?
No, no. We know that since the ratio is very, very small, it only came 1 unit after the molecular ion peak, only 1 unit after. And this means that, and it is in a very small ratio, then we conclude that this is an m+1 peak. It means that it is of the, when the molecule is formed, it formed having only 1 carbon atom that was carbon 13 isotope.
So do you just ignore it?
Yes, we ignore it because we know that this is the m+1 peak.
Okay, okay. Yeah.
Okay.
Yeah, okay.
So, of course, as I told you, the organic molecules are going to be dealt with at the end of the course. Okay.
Yeah,
we are going to take them a little bit in more details. Do you have any question concerning mass spectrum?
No.
Okay. This is the mass spectrum of bromine that I just explained it. Okay. Now, afterwards, we come to atomic orbitals and electronic configurations. We come to the atomic orbitals and electronic configurations. Now, as we said before, that in any atom, we have the positive nucleus in the middle, and we have certain energy shells that are present around the nucleus, at which electrons are present. Okay, we call them quantum shells. We call all these, we call them quantum shells.
Okay.
What do you mean by the name quantum? It means that they are fixed shells. The shells are fixed in their positions. They do not change their position. Every atom has a different quantum shells than the other. It's different from the other. Okay.
Okay.
Now, we call the shells n equals 1, n equals 2, n equals 3, n equals 4. These are the principal shells. We call them principal shells. The principal shells. Okay. Now, when instruments became more and more modern, they were advanced instruments, then scientists found out that these shells are going to be divided into a number of what we call subshells.
Okay.
So at the beginning, we had shells. And when instruments became more advanced, they found that the shells are divided into what we call subshells. Okay, so this is the positive nucleus. And as we said that we have, this is the first shell, for example, this is the second shell. Now we have a third shell. I just want to show you what's going to happen. And this is the fourth shell. Okay, we have, for example, 4 shells. Of course, we have infinite number of shells. But when shells are divided into subshells, how many subshells are divided from each shell? Now, for shell number 1, they are not divided. Also, the subshell is 1. It's only one subshell. But when n equals 2, when the shell was equal to 2, the second shell, we will find that the second shell is divided into 2 subshells. We'll find that the second shell is divided into 2 subshells. Okay, but they are very near in energy. That's why in ancient instruments, they couldn't detect this division because they are very near in energy to each other. The subshells are very near to each other. That's why they couldn't be detected by ancient instruments. But in advanced instruments, they were detected.
So do they both have 8 electrons, or do they have like 4 each?
Yes, every subshell is going to take a number of electrons. Is that your question? Because as I told you, your voice is a little bit low for me.
Oh, sorry. So do the 2 subshells, do they each have 4 electrons?
4 electrons? No. We are going to see that every subshell will have a different number than the other.
Okay.
Not every one of them will hold 4 electrons. No. Every subshell will hold a number of electrons that we are going to know now. Okay? Okay.
Yeah.
Now, for the second subshell, sorry, for the second, it was divided into 2. But for the third subshell, they found that it is divided into 3 subshells. The third shell was divided into 3 subshells. Okay, this is the second subshell. Sorry. Yeah. Now the third subshell is divided into 3 subshells, and the fourth subshell subshell is going to be divided into 4. The fourth shell is divided into 4 subshells. Okay.
Okay. But didn't you say there's like an infinite amount of shells?
Yes.
Okay.
An
So,
infinity amount of shells. Yes. For every atom.
so does that mean there's a difference between shells and orbitals?
Yes. There's a difference between shells. Now we are going to talk about orbitals.
Okay.
Now this is the fourth shell. It's divided into, this is the fourth shell. It's divided into 4 subshells. Okay.
Yeah.
So the first shell is not divided. The first shell is not divided. The second shell, as you see, is divided into 2 subshells, and the third shell is divided into 3. The fourth is divided into 4, and so on. Okay.
Okay.
Now, if I have an electron that is present, for example, here,
Yeah.
I want to describe its position. I say that this electron is present in the third shell in the first subshell.
Yeah.
Okay. Or if I have an electron that is present here in this shell, in this subshell, we are going to say that this electron is present in the fourth shell in the second subshell.
Yeah.
Okay. So you will see that there will be a little bit discrepancy when we say there will be confusion when I say the number of shells in numbers, and when I say the number of subshells also in numbers, then there will be a little bit confusion. That's why scientists decided to call the subshells using letters, not to call them not to give them numbers, but to give them but to give them letters, okay? So the shells will have numbers and the subshells will have letters. So whenever we have a subshell, the first subshell is always going to be denoted by S. The first subshell is called S. And in the second shell, we said that the second shell has two subshells. One of them is going to be called S, and the other is going to be called P. Okay. The third shell is going to be divided into three subshells. The first is going to be called S, the second P, and the third is going to be called D. Okay.
Yep.
The fourth has four subshells, S, P, D, and F. Okay. Now, to differentiate between the S of the first shell and the S of the second shell, or between the P of the second shell and the P of the third or the fourth shell, we have to put the numbers before them. 1S means that it is of shell number 1 and subshell S. Here we are going to say 2S and 2P. This means that these both comes from the shell number 2. Okay, so the number denotes the number of the shell. Here we have 3S, 3P, and 3D. This is the number of the shells. Okay, Matthew, and here we say 4S, 4P, and 4D, and 4F. So we put a letter and we put a number. The number denotes the number of the shell, and the letter denotes the subshell. Now, if I have to describe this electron, I'm going to say it is in 3S, because it is present in the third shell and in the first subshell. So I'm going to describe it that it is present in 3S. Okay? If I want to describe this, what I'm going to say, the position of this electron. Yes?
4P.
Yes, excellent. It's going to be 4P. This means that it is in the fourth shell and in the second subshell. Okay? Now, as you said that more and more instruments are advancing, and they decided or they found that subshells are more divided into what we call orbitals. Orbitals means division of subshells. Okay? So the subshell, which is always called S, does not divide. It contains only one orbital. The S usually does not divide. It consists of one orbital always. Okay, but the P subshell is divided into 3 orbitals. The P subshell divides into 3 orbitals. Okay, as we said, the S does not divide. The P subshell in more advanced instruments was found to be divided into 3 orbitals. And the D is divided into 5 orbitals. Okay, usually odd numbers. S is 1, P is 3, D is 5 orbitals, F is divided into 7 orbitals. Okay, Matthew?
Okay.
Okay, now each orbital can take 2 electrons maximum. Each orbital can take 2 electrons maximum. This means that in the S orbital, it can take only 2 electrons. Here also, since it is only one orbital, it can take 2 electrons maximum, isn't it? In the P subshell, how many electrons can it take maximum?
6.
Yes, excellent, it will take 6. In the third shell, the 3S can take 2 electrons only. The P subshell can take 6 electrons maximum. And the D will take 10 electrons, 5 times 2 makes 10.
Yep.
Okay, here in the fourth shell, we have 2 electrons. In the 4S, we have 6 electrons. In the 4P, we have 10 electrons in the 4D, and we have 14 electrons in the 4F. So if we look here in the first shell, maximum, the first shell takes 2 electrons. The second shell, maximum takes how many electrons?
8.
Yes, maximum it takes 8 electrons. The third shell,
18.
18. The fourth shell,
32.
32. And that's what we know. We say that the number of electrons in any shell, the number of electrons in any shell is calculated from the rule 2n squared, where n is the number of shell. So if the number of shell is 1, if we are dealing with shell number 1, then this means that 1 squared is 1 times 2 makes 2 electrons maximum. If we are dealing with n equals 2, then 2 squared makes 4, 4 times 2 makes 8 electrons. 2 plus 8 plus 6 makes 8. In the third shell, 3 squared makes 9, 9 times 2, 18. So we have here 18 electrons. And here we have 32 because 4 squared makes 16 times 2 makes 32. Okay? So these are the number of electrons that can be held in any orbital and in any shell. Okay, now comes a scientist that is called Hund, and Hund stated that he made us a rule that is called Hund's rule.
Oh, didn't he say you can only have 2 electrons together at a time?
Yes, he said he didn't say that there couldn't be 2 electrons together, but he said, as you maybe you mean that, he said that whenever we are filling these orbitals, we should fill each orbital with an electron first.
Yeah.
And then start to pair them. I know that's what you meant, isn't it?
Yeah.
Hund's rule, Hund said that whenever we are filling orbitals, we usually fill them only one by one. We don't put 2 electrons. If I have 2 electrons to be filled here, no, I don't have to put them here. I should put 1 electron in this orbital and another electron in the second orbital. Everyone should be alone. They should not be paired. Because if they were paired from the very beginning, this means that repulsion will take place between them. We want to decrease the repulsion as much as we can. That's why we should fill each orbital with an electron first, and then we are going to pair the electrons. Okay? So Hund stated that when filling electrons in orbitals, the electrons should be filled one by one, and then it's going to be paired. Okay?
Okay.
That's Hund's rule. Now, how are electrons filled? Are they filled in this order? No, they are not filled in this order. We do not fill 1s, then 2s, then 2p, then 3s, 3p, 3d, 4s, 4p. No, we have a different arrangement when electrons enter through or enters in an atom. They enters, yes, in a sequence, but not especially this sequence. Of course, at the beginning, yes, but afterwards we will find that there are different arrangements. Now, what determines the arrangement of the electrons inside an atom was a scientist that is called Aufbau. So the electronic, when we write the electronic.
I have a question.
Yes.
If the repulsion is that big, why don't all the electrons, why aren't they equally spaced out? So if there's 8 electrons in the second shell, why aren't they spaced out evenly?
They are spaced evenly. You mean the space between the S and the P? Or what do you mean by they are spaced evenly?
In the second shell, why aren't the electrons spaced evenly? Because usually in GCSE, we learn that the electrons are paired together.
Yes.
So that means there's more repulsion than if it's spread evenly.
I really don't understand what you mean by spread evenly, but for they are paired in the same orbital, and even when they are paired, one of them has a spin upward and the other a spin downward. What do we mean by a spin upward and a spin downward? Whenever an electron is rotating in an orbit, okay, it rotates around this orbit in this way, rotating around the nucleus. And in the same way, it is orbiting around itself. We call it is spinning around itself.
Yep.
Okay, so we draw one of the electrons up its arrow. We denote the electron by a spin. So by an arrow. So we draw an arrow upward and another arrow downward. What do we mean by this? It means that even when we have two electrons in the same orbital, one of them is spinning clockwise and the other is spinning anti-clockwise. Okay, so that they do not meet except at a certain moment. A certain moment they are going only to meet. But if one is spinning clockwise, the other is spinning anti-clockwise, then they are going to meet in this part only. And this will reduce the repulsion as much as we can. The second thing is that these orbitals have different shapes. We have the s orbital is spherical in shape. And we said that we have 3 p orbitals. Okay, the p orbital is dumbbell shaped. And we have 3 p orbitals. One of them is along the x-axis. We call it the px orbital. Another one is along the y-axis. We call it the py. And the third orbital is along the z-axis. We call it a pz. Now, these are the shapes of the orbitals. What do we mean by the shapes? It means the probability of finding an electron in the s orbital is in a spherical shape around the nucleus.
Can it be in the sphere, or does it have to be around it?
Yes, it could be here, it could be here, it could be here. We have different probabilities. But when we add all the probabilities, we find it to have this spherical shape. This is the probability of finding an electron in the s orbital. It could be here or here or here or here. But if we sum up all the probabilities, they found it to be in a spherical shape. Okay, when an electron is present in the p orbital, as we said, the p orbital, the p subshell is divided into 3 p orbitals. These orbitals take the shape of a dumbbell shape. Okay, we call this a dumbbell shape. What do you mean by this? It also means the probability of finding an electron here in the px, if we call this the px, because we are free to call this px or py or pz, whatever, because all of the p orbitals are at the same energy. So if an electron is present in the px, then this means that the probability of finding the electron is in this shape. You can find it anywhere in this shape around the nucleus. The py, as it is perpendicular to the px, then you will find it in a different position, and the pz in a third position. So you will see that the electrons are not very near to each other because they are rotating in different orbitals. They are rotating in different shapes. So this will minimize the repulsion between them.
Okay, so where do you find px and where do you find py and where do you find pz?
Px lies along the x-axis. The py is perpendicular to it. You know that we have 3 axes, x, y, and z.
Yeah.
And all of these are perpendicular to each other. If this is x, you can give any name to any one of them. If this is x, this is y, and this is z. So you find 3 different orbitals. This is px. This means that the electron is rotating in this direction. Or else you have py, then the orbital of the electron is in this direction, is perpendicular to the first, and the fourth is perpendicular to them both.
So do you find them all in one go? So all of them together, or is it one or the other?
It depends upon the number of electrons that are present in the p orbitals. If you have only one electron, then this electron is going to be, as we are going to see in the electronic configuration. If you have only one electron, then this one electron will be placed in the first p orbital. So it's the only one that is present.
Yeah.
But
So
if you have, yes.
Would that be in px?
Yes, it will be px by convention. We say that the first one is called px. But if you call it pz, it's okay, because the three p orbitals are equivalent. The three p orbitals have the same energy. They are equivalent.
Okay.
Okay. You understand now, or do you have any other question? Of course, if you have 6 electrons in the p subshell, this means that every 2 are rotating in a certain orbital. 2 of them are rotating in the px, the second 2 are rotating in the py, and the third, the 2 others are rotating in the z1.
Okay. For the so if you have one s and then 2p, would it like have both of them together? So the sphere and the dumbbell?
Yes, yes.
Oh.
That's why when they draw atoms, they draw it like that. You see, sometimes they draw it like this, because all the orbitals are rotating.
Oh yeah. Oh.
All electrons are rotating at different orbitals.
Okay. Yeah.
Okay.
Yep. Okay. Thank you.
Thank you so much. Now, when we like to distribute the electrons on different energy shells or different orbitals, we call it the electronic configuration. Yep. Okay, and who suggested for us the distribution of electrons in an atom was a scientist called Aufbau. That's why they call it the Aufbau principle. Okay, Aufbau made us a diagram, a certain diagram in which we can determine the electronic configuration of any atom. He stated that we should draw the orbitals in the form of circles to say this is 1s, this is 2s, the first shell contains only 1s, the second contains 2s and 2p. The third shell, we said that it is divided into 3 subshells. Sorry, this is 3s, 3p, and in the third shell we have 3 subshells, 3s, 3p, 3d. In the fourth shell we have 4s, 4p, and 4d. In the fifth one we have 5 shells, 5s, 5p, 5d, and we have sorry, this is 4d, yes, and we have also here 4f, we have here 5f, then we have 6s, 6p, 6d, and we have 7s. Okay. Okay. Now we are going to make declined lines like this.
Oh wait, very quickly. So you said there's an infinite amount of shells. Does that mean the periodic table isn't complete?
Yes, it's not complete yet.
Oh.
They are discovering more and more elements, and most of the elements that are done now, they are artificial. All the elements that you found at the 5F, they are artificial. They are man-made. So okay. More and more they are synthesizing more elements because I don't know if you know this, but as the size of the atom increases, it becomes unstable.
Yeah.
And it will be fission. It can be I mean that we have nuclear reactions. Nuclear reactions means reactions between nuclei together. And as we do more nuclear reactions, we can make or we can synthesize more elements. So most of the what we call the transactinides means that they are prepared by man. That's why Yes, we have infinite number of shells, because also when any atom when you excite it using heating or using electrical energy, the electrons are excited to higher energy shells, which are empty, isn't it? So they are raised, electrons are raised to higher energy shells by heating or by subjecting them to electrical energy. Okay.
Oh, okay. Yeah.
Okay. Now, if we do lines, these lines by like this.
Yeah.
So we have 1s, 2s, 2p, 3s, then 3p, 4s, then 4d, 4s, 5s. We have 5d, 5p, 6s. We have 4f, 5d, and so on. So on filling electrons, we usually start by the 1s, and then we go up to fill the 2s, then we go up to fill the 2p, 3s, and then we go up to fill the 3p. But instead of filling the 3d afterwards, no, according to Aufbau principle, we are going to fill the 4s first, and then the 3d, then the 4p, then the 5s, and then 4d, 5p, 6s, then the 4f, and so on. We go along with this distribution. And this means that the first shell to be filled is going to be the 1s, is going to be filled first, and then followed by the 2s, as this diagram says, and then 2p, followed by 3s, followed by 3p, followed by 4s, then followed by 3d, followed by 4p, and so on, 5s, and so on. Okay?
But if you fill 4s before 3d,
Yes.
doesn't that mean one of the inner shells? So one of the inner shells isn't complete?
Yes, we have the three, of course, this is not in your course, but the 4s and the 3d are overlapping together. If we say that this is the 3d subshell and this is the 4s subshell, they are overlapping. This is the 4s and this is the 3d. You see that there is a part that is overlapping between them.
Yes.
So this means that sometimes the electron, not sometimes, but always, the electrons would fill the 4s before the 3d. They say that the 4s has a lower energy than the 3d. They are overlapping together. But the 4s is usually filled first because of other reasons, not for only because they are overlapping, but there are other reasons. Okay? One of the reasons is that 4s and 3d are overlapping. So the electrons would fill the 4s before the 3d. I told you that there are other reasons other than overlapping. Okay? So from experimental previews, they found that the 4s is always filled before the 3d.
Can you give an example of an element where 3d is filled before 4s?
Yes, we are going to take all the transition metals. We do that.
Oh,
no,
okay.
You say the 3d filled before the 4s or the opposite?
Yeah, the opposite. 4s.
Yes, 4s filled before the 3d. Yes, all the transition metals would do that. We are going to take them now.
Okay.
Okay.
But for the transition metals,
yes,
their 3d orbital is already filled.
No, no. The transition metals, they fill in the 3d. They fill the 4s first, and then they start to fill in the 3d.
Okay.
Okay. Now, as we said that the 1s is always filled by 2 electrons. The 2s is filled by 2 electrons. The 2p is filled by 6 electrons. Then 2 electrons, 6 electrons, 2 electrons, 10 electrons. This is the maximum number of electrons that can be filled. Okay, so in order, we should fill the 1s first, and when it is filled, then we can go to fill the second shell. When it is filled, then we go to the upper subshell, and so on. We don't go to an upper subshell except if the first subshell is filled first. Okay?
Okay. Yeah.
Now, we are going to take examples.
Okay.
When I say a hydrogen, and a hydrogen contains only one electron, this means that its electronic configuration would be, I'm going to fill the 1s first.
Yeah.
So I'm going to say its electronic configuration is 1s1. This means, yes.
Okay, yeah.
This means that I fill the 1s by 1 electron. This is the number of electrons. If I say helium, helium-2, then it's going to be 1s2.
Yeah.
This means that the first shell was filled by 2 electrons. If I come to lithium, then its electronic configuration will be 1s2. Now the 1s is filled by its 2 electrons. We can't add another electron, so I have to go to an upper subshell, which is the 2s. So I write 2s and write here 1. This means that I have 3 electrons. If I add these 2 together, I get 3. This is the number of electrons that we are filling. If we go to, for example, beryllium-4, we say 1s2, 2s2. Now the 2s is filled by its 2 electrons. Then the next element, we should go upward to the 2p. For example, in case of boron, its electronic configuration would be 1s2, 2s2, and then we have 2p1. Okay? You will see that in boron, we have 3 electrons in the outermost shell. That's why boron is in group 3. But here we have only 2 electrons in the outermost shell, and this means that beryllium is in group 2. Here we have 1 electron in the outermost shell, which means that lithium is in group 1.
Okay, yeah.
Okay. Now we are going to continue. Carbon 6. So let us do it. Now, if we have here, if we are drawing using boxes, because sometimes he says use boxes to draw the electronic configuration. So here is the 2s. We usually do the last shell only. This is 2s and this is 2p. This means that in case of boron, we have 2 electrons in the 2s. We said that we have to draw the 2 electrons having different arrows to show that they are rotating or they are spinning opposite to each other. One of them spinning clockwise, the other anti-clockwise. And the first electron to be added in the 2p must be placed in an empty orbital. Now we come to carbon 6, which is 1s2, 2s2, 2p2. Then according to Hund's rule, this is the 2s subshell, and this is the 2p subshell. And according to Hund, we cannot place these 2 electrons in the same orbital. This would be incorrect. Okay, so we have to place the second electron in an empty orbital. If we go to nitrogen, then we say, yes.
Can the next electron have a down spin? Does it matter or not?
Doesn't matter which place it is placed in?
No, whether it's up or down. Like
whether its arrow is up or down?
Yeah.
No, it doesn't matter. But by convention, we usually draw the upper one first and then make the opposite. By convention, only by convention. But it doesn't matter whether it is, in reality, it doesn't matter whether the electron rotates clockwise or anti-clockwise. It doesn't matter. Yeah. But by convention, we usually draw it this way. 1s2, 2s2, 2p3 for nitrogen. So we have 2 electrons in the 2s, and we have 3 electrons in the p subshell, so each electron must be placed in a different orbital than the other.
Yeah. Okay.
Now, when we come to oxygen, which is 1s2, 2s2, 2p3, then in this case, we have to pair the fourth electron because the p subshell can accommodate up to 6 electrons. So now we have, here we have 4 electrons. Okay, so we have to draw the first 3 like this, and then the fourth will be paired.
Yeah. Okay.
Okay, now we come to Florine 9. It will be 1s2, 2s2, 2p5. And this means that in the last shell, we have 2 electrons in the 2s, and we have 5 electrons in the 2p. They are drawn 1, 2, 3, 4, and 5. And the last one will be neon 10 in this period, 1s2, 2s2, 2p6, and this means that now the p subshell is completely filled with its 6 electrons. Okay, after we finish neon, we come to sodium.
Yep.
Now, sodium starts a new period. That's why when we make the electronic configuration, we will find it to be 1s2, 2s2, 2p6. Now, the p subshell is completely filled by its 6 electrons. Then we have to go to the upper shell, which is the 3s. So we have to start to fill the 3s by 1 electron. As you see here, we have 3 shells. This is shell number 1, this is shell number 2, and this is shell number 3. And this shows us that sodium is present in period 3. This is in the third period. It started to fill by 1 electron, and so on. We are going to fill from sodium till argon, which has 18 electrons. It will be 3s2, 3p6. Okay. After sodium, we have magnesium 12. It will be 3s2. After magnesium, we have aluminium. It will be 3s2, 3p1. Then silicon, 3s2, 3p2, and so on, until we reach argon to have 3s2, 3p6. Okay.
I thought you said that there's 3 subshells in the third shell.
Yes.
So where's the next one?
It's not present yet because up till now, according to Aufbau principle, we have to fill the 3p first with 6 electrons before we can fill the 4s.
No, I meant like the 3D one.
Yes, there is a 3D, but it's not filled after the 3p. They should fill in this sequence. 1, 2, 3, 4, 5, 6, 7.
Oh wait, so does that mean you fill 3D in the 4th period?
Yes.
Oh.
Yes. After you fill the 4s, you will find that. Yes.
I thought 3D is meant to be n equals 3, not n equals 4.
Yes, it's n equals 3, but as I told you, that since there is an overlap between the 4s and the 3D, then the 4s will fill first and then followed by the 3D. If you look at the periodic table, okay, I'll bring you a periodic table here.
Oh, I'm looking at one now.
Okay, I just want to show you.
Okay.
Okay, if you look here, okay, I'm going to share. Now you can see the periodic table.
Yes.
Okay. Now, as you look here, you will find that this is the first period, this is the second, this is the third that end up with argon. Okay. Now,
yes.
After argon, we have 2 elements, which we call them the main elements. They are present in, they are going to fill, as we are going to see now, in the S subshell. before you start with the 3D, these are the transition metals in the blue color. They fill in the d orbitals. So before you fill in the 3D, this is the 3D, but you fill it, before you fill it, you are going to fill the 4s first.
Oh, okay, okay, yeah.
So this is the fourth period. It starts with potassium and calcium that fills in the 4s first. And then comes the transition metals that they fill also the 4s, but they start to fill the 3D.
Okay.
Okay, and then we go to the 4p. Okay.
Okay, yeah.
Okay, so we go back to our whiteboard. As we said that from sodium to argon, from sodium 11 till argon 18, you are going to fill by a number of electrons that is going to fill 3s2 up till 3s2, 3p6.
Yeah.
Okay, then after argon, we come to potassium. Potassium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and then after the 3p is finished by its 6 electrons, we are going to fill the 4s. This is the order that we should fill with. Then
okay, so does that mean technically in the third shell there's only 2 subshells?
no, there are 3 subshells, which are 3s, 3p, and 3d. But as I told you, the 3d is overlapped with the 4s.
Oh, okay.
And due to other considerations, the 4s is filled before the 3d.
Oh, okay.
Okay, these considerations are not in your course, and even it's not in the first and the second courses of the university. They usually teaches in the third year. Okay, so
Yeah.
we have 3 subshells in the third shell: 3s, 3p, and 3d. But the 3d, as it overlaps with the 4s, and due to other considerations, the 4s is filled before the 3d.
Okay.
But this doesn't mean that we don't have 3 subshells in the 3 shell.
Okay.
Okay,
Yeah.
so the potassium will start to fill the 4s by 1 electron. And the 3d is empty. We can write it here. We can write the 3d here and leave it empty.
Yeah. Okay.
Okay, now comes the calcium, which is 20. The electronic configuration will be 1s2, 2s2, 2p6, then 3s2, 3p6, 3d is empty. We start to fill with 4s2.
Okay.
Okay, after the 4s is finished by its 2 electrons, then we go to the 3d to start to fill it. And this is the start of the transition metals. Starting by scandium 21, we are going to fill the 3d. Okay, Matthew?
Yeah.
Understand it now?
Yeah.
Okay, I think that we have to end up here and to start the electronic configuration of transition metals, inshallah, next week. Okay?
Okay. Yeah.
Is there any question you have for today?
Do you want me to do any homework?
Yes, I can send you homework to do it. I can send you homework. I'm going to send it on your mama's email. Okay?
Okay. Yeah.
Okay. Thank you so much, Matthew. It was a pleasure to be my student, and inshallah meet you next Sunday. Okay?
Okay.
Thank you so much. Bye.
Thank you to you.
Thank you.
Bye-bye.
Bye. Bye. Bye.